Weak bases. Before we look at weak base, we should quickly review strong acid. Strong acid dissociate or dissociated, which means ionized completely in solution of water. This is generic equation for acid dissociation. Ka is the acid dissociation constant. If we write down the I's, initiation, any changes, and at equilibrium, initially we have 0.1 mole of concentration of acid, no H plus ion and no A minus. Because the stoichiometric mole is 1 to 1 to 1, so we're going to dissociate all the acid concentration, so that will be minus 0.1, and we're making a proton ion, so the proton will be 0.1 because all of them has been converted into H plus and A minus, so therefore you will have plus 0.1 of A minus. At equilibrium, we would have no more HA, we would have gained 0.1 H plus and 0.1 A minus. pH will be equal to minus log base 10 concentration of H plus, therefore pH equals minus log base 10 0.1, pH equals 1. Now let's remind ourselves of weak acid. A weak acid will partially dissociated or ionized in solution of water. This is the equation of an acid. This will be a weak acid, and that will be a conjugate base of a weak acid. Not all the acid is converted into H plus and A minus. Very small amount is converted into H plus and A minus. So now we do the I's, initial state, any changes, and at equilibrium. Initial state, we have a concentration of HA, 0 concentration of H plus, 0 concentration of A minus. During the changes, we have lost minus X value, and we've gained plus X of H plus and plus X of A minus. The concentration of H plus will be equal to concentration of A minus. Same amount will be produced. That's why it's X and X. Because we've lost X, so we do 0.1 minus X. That's what we get here. And this will be the X that we've gained and the X we've gained at equilibrium. Let's write the Ka value. This is the acid dissociation constant, and that will be the product over the reactant, concentration of H plus, the product, and A minus divided by the concentration of the acid, HA. Do remember the concentration of H plus is equal to the concentration of A minus. Okay, we know that concentration of H plus is X and the concentration of A minus is X at equilibrium. The Ka value is at equilibrium. And so we can say, well, concentration of acid times Ka is equal to the concentration of H plus X times concentration of A minus X. So we know X equals H plus, therefore X squared equals Ka times concentration of HA acid, which implies that X equals to root Ka times concentration of HA. Therefore, HA is equal to 0.1 minus X. If X is less than 5% of HA, we can then ignore the X. HA equals 0.1. H plus equals to root Ka times the concentration of HA, which means that the concentration of H plus of a weak acid depends on the value of Ka and the concentration of the acid, HA. Therefore, pH equals minus log base 10. We replace the H plus with root Ka times the concentration of HA. So if you want to find the pH of a weak acid, this is what we use. We need the Ka and the concentration of the acid. Let's quickly look at strong base. Strong base will completely dissociated or ionized in solution of water. If we're looking at the conjugate base of an acid and we have to react it with water, liquid, and the Kb, the base dissociation constant, will give you OH minus because it will steal H plus from the water and to form HA. And if this is the base, that will be the conjugate acid. If we write down the I's, initial state, change at equilibrium. At the initial state, the concentration of base is 0.1 and OH minus is 0. HA is 0. And the change will be minus OH minus. Because it's a strong base, all the base here will be converted into OH minus and H plus, which means that we're going to have a gain of 0.1 and a gain of 0.1 for the acid, conjugate acid. At equilibrium, 0 of A minus is left because all is being used, and we got 0.1 of OH minus and 0.1 of HA. Now we can find the POH, which equals to minus log base 10 OH minus concentration. That equal to minus log base 10 0.1. POH equals 1. But pH plus POH equals 14. Therefore, pH equals 14 minus POH. pH equals 14 minus 1. pH equals 13. To find the pH of a strong base, we need to find the POH first using that, and then we use the pH plus POH equals pKW. That's the dissociation constant of water, and then we take it away from the pH then is 14 minus POH. Now to find the weak bases, or weak base are partially dissociated or ionized in solution of water. This is the generic equation of a weak base dissociating in water. The A minus is the conjugate base of a weak acid, and this A minus must react with water, and that'll be K, that means the base dissociation constant, Kb, equals to OH minus plus HA aqueous. This is conjugate acid. Since that's a base, that'll be the conjugate acid. The difference between them is H. The first thing to do is to write ice, initial state, any changes, equilibrium. Next point is to write concentration of the base, or 0.1 in this case, 0 for OH minus and 0 for HA. The next point is to write the small concentration of A minus will dissociate, so let's call that plus X gain and plus X gain and minus X lost or fraction lost to make the OH minus and HA. At equilibrium, we have 0.1 minus X that was lost and X gain. So that means the concentration of OH minus is X and the concentration of HA is X. So we can write the expression for Kb, which is the concentration of OH minus times concentration of HA divided by the concentration of A minus. And that equals X squared, because that's X times X, the concentration, divided by 0.1 minus X at equilibrium. So these are the values at equilibrium, and that's roughly equal to X squared over 0.1, because we're looking for the concentration of X. So we can approximate X here to be so small, it will be equal to 0, because the percentage of X is less than 5% of the A minus, the base concentration. Because we know that Kb equals X squared over 0.1 minus X, which is now approximate to X squared over 0.1. So we can, and that's the concentration of A minus 0.1. We can now say the concentration of A minus times Kb equals X squared, and roughly taking square root on both sides, X equals root Kb times concentration of A minus, and we know what X equal to really. X equals to concentration of OH minus. Concentration of OH minus equals to root Kb times concentration of A minus. It shows that the concentration of OH minus depends on Kb and the concentration of the base. Now we can find the POH, which is minus log base 10 of the concentration of OH minus. POB will be equal to minus log base 10 root Kb times concentration of A minus, because OH minus concentration is root Kb times A minus, which we've replaced that with that here. To find the pH, we need to use pH plus POH equals 14. pH equals 14 minus POH, and that's how we find the pH of weak bases, weak base. Example, what is the pH of a 0.1 molar ammonia solution with Kb equals to 1.75 times 10 to the power minus 5 mole per decimeter cube. Weak base plus water dissociate to give a conjugate acid plus OH minus. The weak base here is ammonia plus water, and Kb, base dissociation constant or base ionization constant, will give you ammonium plus an ammonium ion, NH4 plus aqueous, and OH minus aqueous. We do the I's initial concentration. You're given that 0.1. It's a weak base, so 0 initially, 0 initially. We take away X, we gain X, we gain X, because the ratio is 1 to 1 to 1. At equilibrium, we got 0.1 minus X, that's what we got, and we got X value or concentration of the conjugate acid, and we got X value of OH minus. We can write the Kb expression, the concentration of ammonium ion times the concentration of OH minus divided by the concentration of ammonia, the base. We know that's X times X, that's X squared, 0.1. Because we're looking for X, we can assume that X is 0, and so we get 0.1. And that is if X value is less than 5% of ammonia concentration. Now we can find the POH, which equals to minus log base 10 root Kb times concentration of ammonia, and that equals to minus log base 10 root 1.75 times 10 to the power minus 5 times 0.1 to give you 2.9. So the POH is 2.9. We're looking for pH. To find the pH, we have to use pH plus POH equals 14. And then making pH the subject, that will be equal to 14 minus 2.9, and that equals to 11.1. So the pH is 11.1. Here is another question. What is the Kb of a weak base A minus if the pH of a 0.1 molar, that's mole per decimeter cube, solution is 10.2? The generic expression for the weak base is, this is the base reacting with water, give you OH minus plus HA. We always have to react it with water in this case. Kb, base dissociation constant, will be equal to the OH minus concentration times the acid or conjugate acid concentration divided by the base A minus concentration. To find Kb, we need concentration of OH minus and the concentration of acid and the concentration of A minus. Because the pH equals 10.2, POH will be 14 minus 10.2, and that equals 3.8. We know that the OH minus concentration will be equal to 10 to the power minus POH, which equals to 10 to the power minus 3.8. Let's write down the I's. Initial state, changes, equilibrium. At initial state, A minus is 0.1, OH minus is 0, HA is 0. At the change, we take away the concentration of the OH minus that is being created. So the OH minus concentration is plus 10 to the power minus 3.8. Likewise, the concentration of the acid HA, conjugate acid, will be 10 to the power minus 3.8. We take away that from the concentration of the initial base, 0.1 minus 10 to the power 0.8. At equilibrium, 0.1 minus 10 to the power minus 3.8 for the base, and OH minus is 10 to the power minus 3.8 because we calculated that here, and the acid, conjugate acid, is 10 to the power minus 3.8. We're going to plug those into the value for Kb. For Kb, we now put those values in the equation here. We populate it, and this is 10 to the power minus 3.8 squared, because that times that, and divided by the concentration left at equilibrium for A minus, which is 0.1 minus 10 to the power minus 3.8. We have to include the 10 to the power minus 3.8 in the denominator here because we're not looking for concentration, we're looking for Kb. So in this instance, whenever we're finding Kb, we include the value here for X. But if we're finding concentration, if we're finding X, we can eliminate that value so that we don't have quadratic equation. and the value of Kb is 2.52 times 10 to the power minus 7 mole per decimeter cube.